Hi, welcome to Accelerated Engineering. Today's tutorial or workshop is going to be how to build a rudimentary system solver. So in this case, I'm going to show you how to build a solver that will take a basic equation, in this case a 3-variable equation, and when given any set of 2 variables, it will solve for the third. And if given all 3 variables, it will check and make sure that that is a valid solution. We're going to implement this solution into a Lambda function that can then be called anywhere else that you want on any other worksheet, really, to solve this equation. So without further ado, let's get started. The goal is to solve the voltage equals current times resistance law, or Ohm's law. Although really this shape of equation is shown in many other places. We could equally be solving force equals mass times acceleration. We could be solving power equals voltage times current, or what's another one? Momentum, the other P, equals mass times velocity. Right? Any of those ones would be solved equally well, but we're going by voltage is current times resistance, Ohm's law, because in the real world I'm an electrical engineer and that's how I'm going to do that. Okay, this is our goal. How are we going to go about this? To make this easier to visualize, I'm going to draw some steps out long form, starting with let's get some places for variables set up. Resistance. We'll hold some values over here because I think we're going to want them later. Now let's see. A valid solution is 6 volts is equal to 3 amps across 2 ohms. 2 times 3 equals 6. That makes sense. I'm just going to hold on to those variables for a bit. Okay. Let's start writing a function. I'm going to write it over in this cell here. So to start with, I want a lambda function because I would like to later turn this into a function that I can call from other places. So for my lambda function, I need as my input variables, I'm going to say that my input variables are one called voltage, one called current, and one called resistance. There we go. For the time being, I'm going to just say that my output value is 1 so that this compiles properly. And for right now, I'm actually going to set it up so that my voltage, current, and resistance variables are already fed into this. Even though there's no calculation occurring with these variables, I'm just going to feed it to the equation or to the function so that they are there. Make sure that that compiles or is fine, and it is. I would like to just space this a little bit differently to increase the human readability. Okay. We have the lambda function primed. The next step that I always do for basically anything inside of a lambda function is to set up a let function. And I use let functions because they get to be very flexible in their implementation and what you do inside of them. I also always space my let function out so that it's human readable and initiate it by giving it a test value equal to 1 and then telling it to output test. And if I hit enter and this works fine, then good, everything's going. This solves a whole lot of troubleshooting later. I will just have it always output that test value. There we go. I'm just using 5 spaces as kind of my indent because it keeps things easy later. Okay. What's the first thing that I need to do? Well, in order to solve for a missing variable, I need to know which one is missing. So how can I do that when I have a handful of variables here? Well, I guess the first thing that I need to do is I need to tell this function that all of these variables are optional by enclosing them into square brackets. This lets Excel know that any of these variables being fed into this lambda function may or may not be there, and that's okay. Otherwise, it'll throw errors all the time. So knowing that, how can I detect which variable is missing? Well, it turns out there's a really handy way to do that. If I said that the value of like whether or not voltage is present is equal to 4, and whether or not current is present is equal to 2, and whether or not resistance is present is equal to 1, I can take the sum of these indicators. It will always equal a number from 0 through 7, and no matter what number it is, I can reconstruct which variables are present and which ones are missing. And the way that that looks in a formula is I would say if this cell is blank, well, maybe not even if it's blank, well, we'll start with is blank, then I would like you to equal 4. And if not, I'd like you to equal 0. So if voltage is missing, this will equal 4. Otherwise it equals 0. Let's just check that. Yep, works just fine. I'll copy and paste to speed things along, and then just change the internal values to 2 and 1 respectively. Okay, so if, oh, and then my indicator, of course, would be a sum function that just sums these three up. 0, nothing's missing. 4, voltage is missing. 2, current is missing. And 1, resistance is missing. Perfect. Okay, that does what I want it to do. Now, there's going to be a little bit of a problem is if one of these things equals 0. If one of them equals 0, I think we'll still go with a solve. We'll end up with like zeros and infinities and it'll be a problem later, but I'm going to leave it like that for now. That covers if the input is blank. So let's just take a moment and implement this into my new lambda. I'm going to call this next variable outputSelect because this is what we're using to determine what's going on. I'll say this is equal to if is blank voltage, then it equals 4 or 0. Okay, and then I'm going to add to that if is blank current to 0 plus if is blank resistance 1, 0, comma at the end. Now I could also do this with a sum function wrapping everything in this line and separate all of the if functions by commas instead. And that is another perfectly valid way of solving this. I just don't like the way that that looks for a couple of reasons. One is it adds an extra nest of function, which can cause problems later if it's trying to keep it human readable. And the other one is that if these conditions become too long, or if there are too many conditions, because this does scale up, it becomes really easy in this shape to, using Alt-Enter to break the line, take each of the different components and line them up like this, which again just keeps things really readable. It's easy to see how these are the same, how they add up, and how it changes. Okay, let's hit enter and make sure that that compiles. Nope, it didn't like it. I've got too few arguments. There we go, just one too many parentheses. Perfect. Okay, next thing that I need to do is generate an output variable. So I will call it soup, I will call it output, and then have this operate as a switch function based on outputSelect. So as a reminder, what the switch function is going to do is it will take whatever the value is of outputSelect and then do something. Once we have outputSelect, we know which variable is missing, so we can code these different solutions into a switch function and always pick the right one. So I'm going to do these in numerical order. We'll say the first one is 0, and then we're going to do something. And we won't decide what quite yet. the next one will be 1, and then we're going to do something. And actually what I'm going to do for right now so that it compiles properly is I'm just going to make it always output a number, a not available error, because, oops, so that I don't get too many of those. Expand this, go, that'll be for 2, 3, 4, 5, 6, 7. Then while I'm thinking about it, I will close the switch function, change all of these values, and hit enter to see if it compiles properly. Nope, that means I've got a comma somewhere. Yeah, missing the comma at the end of the switch function, reminding it that everything between here and here gets assigned to the variable output, and that means that it needs a comma after it so that it outputs my test variable, which is equal to 1. That'll compile. Good, 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 good. Okay. Well, let's see. If we get the number 7, that means that we are missing all of our variables. We can't solve that, so I'm going to leave that as an error. If we get 6, it means that I'm missing both voltage and current. We can't solve that, so it'll stay an error. 5 is missing voltage and resistance, so that's an error. But 4 means that we're just missing voltage. And if we just look at this equation, voltage is equal to current times resistance. So we can replace the value in number 4 with just current times resistance. And that's it. If I hit enter, I should get a value. Now let's just check that. I want to have, instead of outputting test, we're going to output the output variable. And I got a not applicable. Oh, right. Because, well, this function, the solution for number 4, is well defined. Of course, it's expecting to see a missing voltage value. So let's get rid of voltage. And there we go. 6 pops out. That's exactly what we expected. That's exactly what we wanted to have happen. Perfect. Okay, if we get a 3 for output select, we're missing both resistance and current. That's not possible to solve, so we'll leave it as an error. For 2, that means that we need to solve for current. So here, let's see, V equals IR. The other shapes of this would be that current is equal to voltage divided by resistance, and resistance is equal to voltage divided by current. Check that and make sure I did that correctly. Divide both sides by R, check. Divide both sides by I, check. Okay, so case number 2, solving for current. Current is equal to voltage divided by resistance. Perfect. Case number 1, solve for resistance. Resistance is equal to voltage divided by current. And the last thing that I think we're going to do is, in the 0 case where we're actually fed all 3 variables, I'd just like this to do a check for me. I'd like it to say, if voltage equals current times resistance, return true, do that in all caps, and if not, return false. And that'll just be a nice check. So what I expect when I hit enter is that this is going to return the value true, because we have a valid solution for our system for our equation. Perfect. If I change a value here, it'll say, nope, that's not a valid solution. And if I get rid of any of my variables, then it always returns and solves that system. Perfect. What happens if I drop one and add a wonky number here? Quick check, 456, well, 3 times 152 is 300, plus 150 plus 6, perfect, 456. Yep, so that is working just fine and dandy. And if I make any of these blank, it works good. Okay. So that is working the way that I wanted it to. Let's convert this into a lambda and then make sure that it still works. So we'll go copy, shift over to formulas, the name manager, start a new one, and we're going to call this solve Ohm's law. The comment will be this solver returns the missing value that satisfies Ohm's law V equals IR. What this refers to is that entire chunk of string that we just got, which will be ugly. Okay, that's in place. Close that and do a side-by-side. This equals solve Ohm's law, and we'll input a voltage, and a current, and a resistance. There we go. That equals true. If I remove this one, perfect. Remove this one is good. If I remove 2, it throws an error. Add an extra one here. Yep, this is working just fine. But wait, we said that those inputs were optional. So what happens if we throw it, what happens if instead we decided that, you know what, we just didn't give it one of the variables? It still solves it. Why does it do that? Well, it does that because we told it that these things were optional, and it assumes that if it's not there, it's blank. So we've got our bases covered there. What happens if we did something troublesome, like fed this as 0 value? Well, if we feed it some 0 values, it's going to say that actually, oh wait, that actually is a solution. That's not. And if we get rid of a value, we get a divide by 0 error. Do we want to deal with that? Maybe not in this one. This is a pretty rudimentary one. Now, the reason why I like setting things up like this is because it can be incredibly flexible. For example, I'll just put in a solvable system again. So, for example, if I always wanted to know or have my units declared, which you can do, I might say voltage divided by current is always going to give me an output in ohms. So I might actually insert a value here. I like to include my my units in square brackets. So I'm going to do that. I'll put voltage divided by resistance gives me current in amps, and current times resistance outputs a voltage in volts. There we go. Now it will always spit out the right value. I'm actually going to make this even one better. Let's take a symbol that I like. Whoops, cancel. I'm going to put it in the right place. Where's the ohms symbol? Should be in... This will be fun. Am I going to be able to find it? Where's my Greek? Greek extended. There we go. There's some omegas. There's ohms. Ohms with apostrophes. I want just a little ohm symbol. I just want a little omega. It's because it's in the Greek extended. There it is. Found it. Okay. I want that symbol right there. I just hit Control C, and I'm going to paste it directly into here. Perfect. There. That'll output 2 ohms. Put that in. Be true. This shows that it's going to be 6 volts that's missing, and 3 amps is missing. That's great. So that's one of the ways that these can be flexible, and anytime that you need to update your Lambda function, it's just a matter of copying and pasting all of the correct values into the Lambda function. By hitting edit, I always drop in here and go control, sorry, no, I forgot, I can't control A, backspace, paste, and done. And now my existing function is going to be automatically updated to do exactly the right thing. And that's how you would build a basic solver for a 3-variable equation. You can do it with 4 to solve a ratio, for example, and the most that I've ever done so far is with the triangle solver, which solves a 6-variable system. For any 3 angles and 3 side lengths, it'll solve the remainder for a triangle. Anyway, there's a whole video on that, which I'll probably link in the end card, which should be popping up shortly. Anyway, thanks for tuning in to Accelerated Engineering for this workshop. I hope that you find all sorts of uses for these Lambda equations and system solvers.